Hi over there, it's Physical Sciences again. It's Saturday Extra. My name is Tinyiko Kosa and I welcome you once more to be part of this lesson until the end. And today we're going to talk about chemical equilibrium. Now, having spoken about rates of reaction, this links quite well with the section on chemical equilibrium. So we're bringing it in, one after the other so that you understand how they link, and it makes it easier for you to even understand equilibrium reactions better when you have done rates of reaction. So we will have this lesson here. Firstly, we will be looking at some terminologies involved with, in regard to chemical equilibrium. We will also look at how we can represent chemical equilibrium making use of graphs. We will also look at something called equilibrium constant. We call this Kc. That is the symbol for equilibrium constant. And we'll also look at Le Chatelier's principle. We will unpack all these things. Don't worry for now. We just have to start from the beginning and look at these terminologies and unpack them. You will understand them as we move on with the lesson. Let's start now. In chemical equilibrium, we talk a lot about things like forward reaction, reverse reaction, reversible reaction. Now, what are these things? When we say forward reaction, we are actually saying, remember that when we did chemical reactions and rates of reaction as well, we said chemical change and rates of reaction, we said these two here, if we've got A and B reacting, say the product is C and D, we were saying that these are our reactants. I think you will remember that. And then we said that these are our products. Okay? So we've got products there. Okay? Now, this is an arrow which is used. Remember, we don't use an equal sign in chemical reactions. We make use of an arrow. Right. Now, from A and B reacting to give us C and D, we're saying that this is a forward reaction. In other words, it's moving from left to right. So that becomes a forward reaction. Okay? Forward reaction, like it's written there. But then say instead of A and B reacting to give us C and D, what we see is that C and D, this is the second part, is actually reacting to give us A and B here. Then in this case, these become our reactants, and these ones become our products. Okay? Now, because A and B giving us C and D is seen as the forward reaction, then C and D reacting to give us back A and B would be referred to as the reverse reaction. Okay? Now, from here, from these two here, we can move on to what we call reversible reaction. If A and B is able to give us C and D, and at the same time, C and D are also able to react and give us A and B, which is shown by this second one here, then this reaction here is reversible. And what is meant by that reversible reaction? It means that when we have A and B together, it means that when we have A and B together reacting, giving us C and D, we are seeing that instead of writing again that A and C and A and B is reacting, it's actually give the products and then the arrow to the left. With that, we can actually just write the second arrow there to show that C and D is also reacting to give us what we started with. And then this becomes a reversible reaction. It can go forward, it can also go backwards. Hence the double arrows to the right and to the left, forward and reverse. That's what it means. So reactants form products in a forward reaction. A and B gives us C and D. And products form reactants in a reverse reaction. C and D gives us A and B. Okay? Now, when we have that, this can only happen when we have something called closed system. Remember, we're still dealing with terminologies. We also talk of closed systems in chemical equilibrium. What would be a closed system? A closed system would mean that no matter, now this is not a literal meaning of the word in terms of the language English, but matter here refers to substances, refers to atoms, molecules, all right? So no atoms, no molecules will either enter or leave the system because the system is closed. So we're talking about a closed system because no matter, no material, no substance, no molecule, no atom is leaving or entering this system. It is a closed system. All right, so that's one of a very important term or terminology that is used in chemical equilibrium, and understand what it means. We also have this one, dynamic equilibrium. Dynamic equilibrium, when do we have that? We have this when the rate of the forward reaction equals the rate of the reverse reaction. Now this is very important because this is actually the pillar. This is what is saying about chemical equilibrium. It is a state in a reversible chemical reaction where the rate of the forward reaction equals the rate of the reverse reaction. This means that how fast the reactants are reacting to give us the products is equal to how fast the products are reacting together as well to give us back our reactants. So that is a state of chemical equilibrium. So you must know that, you must understand that. Okay, now we can represent or we can have different types of this dynamic equilibrium. This dynamic equilibrium could be phase equilibrium. For example, when you have got water in the liquid form boiling to give us water in the gaseous form, and say it's boiling in a closed, like I said, closed system now. So boiling in a closed, airtight, okay, flask or container like that. The water molecules are boiling. We know what happens when water molecules boil. They evaporate in the form of gas. And when reaching the lid here, when reaching the lid up here, the water molecules will condense because the part here on top of the lid, it's colder than the inside. So they condense and that water drops back as water molecules, as droplets of water now, not as steam or form in the, or not as steam or water in the form of gas. So it's droplets of water coming back. So there is a time when the molecules that are actually converted into gaseous form equals to the number of water molecules that are converted into liquid form. So at that moment, we have what we call phase equilibrium. Liquid turning into gas and gas turning into liquid at the same rate. Okay, so that's what we have, and that gives us the phase equilibrium. But then we also have what we call chemical equilibrium. Chemical equilibrium would mean that if we have chemicals A and B reacting together to give us C and D, the rate at which the forward reaction takes place, in other words, how fast A and B are reacting to give us C and D, at that point when C and D react equally fast to give us A and B, at that point we have reached a state of chemical equilibrium. So the rate of forward reaction equals rate of reverse reaction. And at that time, we have a chemical equilibrium that has been reached. Okay? Now, let's move on to the next stage. Now, representing chemical equilibrium, making use of graphs. Now, let's look at some theoretical reversible reaction. We're calling it theoretical because we don't have a chemical in the real sense called A or B or C or D. So this is theoretical, something just to help us understand what is happening. Okay, now let's say these are in a closed container. So once we have a closed container, it means we have what I referred to earlier on as a closed system. Okay, so we've got a system here that is closed. Nothing can go in, nothing can come out, so the system is closed. And in that situation, we can have a state of equilibrium because the system is closed. Okay, so say we have that one, and let's say we are to look at what happens in terms of the rates of reaction. Now, with the forward reaction, we know that it is A and B reacting to give us C and D. Okay? What is the initial rate of the forward reaction? Okay? Now, the forward reaction we need to know. Let's look at this graph here. We need to know that with the forward reaction, we're starting with the reactants already. And because they are together, it means they are starting at some rate already of reaction, okay, with time. But then with the products being formed, the products are starting at zero because we have got nothing of the products being formed before the reaction takes place. So now let's look at what happens to the rate of the forward reaction. Remember, we're looking at the rate of A reacting with B to give us C and D. Okay, so that's what we're looking at. For the forward reaction, we see that they react, A and B react to give us C and D. The rate takes place faster, so at first up there, but slows down as time goes on, and there will be a time when the rate is going to level up like that. Okay, so it levels up. In other words, the rate sticks to a particular value and doesn't change anymore, okay, with time. Now with the reactants, with the products, we know that with the products A and C and D, remember that the reaction is like this. We've got A plus B giving us C and D. Now the reverse reaction, it means C and D are now reacting together. As they react together, C and D, okay, they are forming, and therefore their reaction rate increases with time. It increases with time, slows down as it moves on until the rate now, the rate of the reverse reaction now equals the rate of the forward reaction. This should be a single line moving like that because the rates are now equal. Okay? Now, what we are trying to say here is that at this point here, the rate of the forward reaction, remember the brown color line gives us the forward reaction. This is the forward reaction rate. Okay? And then this color here, I'm so much of a colorblind person, but I think this could be somewhere between some purplish color. this would be representing your reverse reaction rate. In other words, your C and D reacting to give you back A and B, reverse reaction rate. Okay? Now, so at this point here, which is this point here, the rate of the forward equals the rate of the reverse. Say here it was at 0.5 mole per second. Remember, this is the unit for rate of reaction, mole per second. Okay? At that point, they are both the reaction, the forward and the reverse, are having the same rate. So from this point here, if you like, to that point there, let me call this one T1 and that one T2. Between T1 and T2, a state of chemical equilibrium is reached. In other words, from that time of T1 to T2, our chemical reaction here has reached chemical equilibrium. Okay, so we have reached a state of chemical equilibrium there. Right. Now that is what it means, okay? So the initial rate of the forward reaction was quite high and it drops down. And the initial rate of the reverse reaction was actually very low from 0, and we see it building up, increasing until it reaches that point there where they were the same. Let's look at it. This is the reverse reaction. A and B, in fact C and D reacting to give us, you see that arrow there pointing to the left to give us A and B. That is your reverse reaction. Now what is the initial rate of the reverse reaction? The initial rate of the reverse reaction was 0 mole per second because there was nothing, okay? There was no reaction happening before the A and B reacted to give us the initial substances of C and D, or amounts of C and D. All right, so that's what it was before. Okay, now let's have a look at some example here. Example 1. A closed 1 cubic decimeter container has 4 moles of nitrogen dioxide at 30 degrees Celsius. The molecules combine to form the dimer, dinitrogen tetraoxide. Now that is that molecule there. This is nitrogen dioxide giving us the dimer there. And after some time, chemical equilibrium is established as represented by the following equation. Right, 2N2, reversible. Remember the double arrow tells us that this reaction is reversible, giving us N2O4. At equilibrium, there are 2 moles of nitrogen dioxide present. Draw a sketch graph to show how the concentration of reactants and products change during the reaction. Draw a sketch graph to show how the concentration, now this time we're talking concentration of the reactants and the products, not the rates. Now how is that going to be drawn? Remember, we're starting with 4 moles of nitrogen dioxide, but at equilibrium we have got 2 moles of nitrogen dioxide. Okay, now we are not told at what time equilibrium is reached. All we are told is that with nitrogen you're starting with, so if I've got nitrogen here, if then this color represent nitrogen dioxide, NO2, okay? I'm starting at that point. But with time, I'm told that 2 moles are remaining at equilibrium. So say equilibrium was reached at that point. So 2 moles at that point, okay? And equilibrium is reached. If equilibrium is reached there, it means from there until the end, I've got a line like that leveling up. Equilibrium has been reached. So from here downwards, what I will have is a curve like that for nitrogen dioxide. Why do I have it like that? Because nitrogen dioxide is actually the reactant. It's being consumed. It's getting less and less in terms of concentration in mole per cubic decimeter. And I'm told that at equilibrium, it is 2 moles that are left. That means that 2 moles have been used up. Now, there's something very interesting that I need to show you. Let's go back to the equation. There is something called mole ratio or molar ratio. What does this thing tell us? From here, this is the ratio, or the stoichiometric factor gives us the ratio. We see that 2 moles of NO2 will yield, what is the stoichiometric factor there? Because there is no number that we can see there, we know that the number there should be 1. So the ratio there is 2:1. So for every 2 moles of nitrogen dioxide, I will produce 1 mole of the dimer, dinitrogen tetraoxide. Okay? Now, if I start here, I start with nitrogen dioxide, I start with 4 moles. Okay? I start with 4 moles. Start with 4 moles of nitrogen dioxide. And I'm told that at equilibrium, I'm left with 2 moles. Okay? If I'm left with 2 moles at equilibrium, what has happened? 2 moles have been used up. Now, if 2 moles have been used up, I'm told by the ratio here that if I use up 2 moles, I will produce 1 mole of nitrogen or of the dimer. So, because 2 moles have been used up, according to what has been given to me, 1 mole of this has been formed. That's what it means, okay? Therefore, it means when I come to look at the nitrogen or the dinitrogen tetraoxide, okay, where we started with no concentration, if you like, because this was the product, okay? It was nitrogen dioxide actually reacting, molecules reacting together to give us the dimer. I'm starting there at 0. But if 2 moles have been used of nitrogen dioxide, half of that should be formed, and half of that will be 1. So if that is 2, this will be 1, and that will be 3. So 1 of this would have been formed. And the equilibrium will be reached at that point, so I'll have that. So from there, this way, I've got a line, a horizontal line that shows that a state of equilibrium has been reached. Nothing is changing there in terms of the concentration of dinitrogen tetraoxide. So the reaction, the change in concentration has been in that form. Okay, maybe that has not been much of a nice one. Let me just start this line again. So the reaction rate increases and reaches a state of equilibrium at that point. Okay, so that's the line I would have. Okay, now, so this will be, that one is for nitrogen dioxide, and this one will be for dinitrogen tetraoxide. Okay, so this point here, these dots should actually be exactly at the same point. At this point here, let me call it T1. At T1, from T1 this way, this is a situation where the state of chemical equilibrium has been reached. Okay? The chemical equilibrium has been reached at that point. Chemical equilibrium has been reached at that point. From T1, let's say here the end is T2. Okay? Chemical equilibrium has been reached at that point. Right, so I think this was the 2 graphs that we've worked on now. Should be interesting. You should be seeing what is happening there. the concentration decreasing, one concentration increasing, okay? And also the rate. Remember, differentiate between the two graphs. The first graph was talking about the rate. The rate is to be the same at the end. So the two graphs come together. That's why they come together there and then have that horizontal line at the same point or the same level. But with this one, you will see that their horizontal lines are not at the same level because this one is a graph of concentration versus time. And therefore, we'll have a certain concentration of NO2 at the equilibrium, and we'll have another concentration of N2O4 at the equilibrium. They won't necessarily be the same. Okay. Right, let's move on, and let's look at something called equilibrium constant. Okay, now equilibrium constant is, like I said earlier on, the symbol for it is Kc. This relates to a chemical reaction at equilibrium, okay? And it tells us actually, it can actually tell us the degree at which our equilibrium has shifted. Is it more to the right or more to the left? Things like that. But we'll learn more about that as we move on. Okay? Now, if I have a reaction, say, between A and B, and this is a reversible reaction, so it goes forward and backwards, and I produce C and D. Okay? And suppose that when I am to balance this chemical equation in equilibrium, and remember this is just a theoretical one, a hypothetical one. If I'm to balance it, I'll have a factor to balance A here, and let me call it small a. I'll also have a factor there to balance B, let me call it small b. The same thing for C, and the same thing for D. Okay? Now, the equilibrium constant, okay, can be calculated using that. We can calculate that equilibrium constant using this, and for us to calculate for it, we need to know the concentrations of our chemicals, which will be A, B, C, and D. So we need to know the concentrations of A, B, C, and D. And these concentrations are not just any concentrations of A, B, C, and D, but these are concentrations of A, B, C, and D at equilibrium. Okay? So concentration of reactants and product at equilibrium. We can only calculate if we know those at equilibrium. Okay, now let's quickly have a look at this. Now here is an equation that I have just written down earlier on. Okay, and it is in equilibrium. So if we consider this equation here, for us to calculate for the Kc, this is how we do it. Remember I said this small a, the small b, and the small c, and small d are balancing factors. Okay? Balancing factors. For us to have that chemical equation balanced, we put those factors. And these balancing factors are also called stoichiometric values. Okay? So there is one nice term. You don't have to crack your skull trying to get it down, to sink it down your mind, but just know that these factors are also called stoichiometric factors. Okay? Right. Now these numbers here, when we write down the Kc expression, so this is called the Kc expression. So this is for the general or the theoretical chemical equation that is in equilibrium. A plus B giving us C and D. When we write it down, look at it. We said we look at chemical, we look at the concentrations of the chemicals. The symbol, this symbol here, big brackets, open and closed, it's a symbol for concentration. Allow me to write conc for concentration there. That's a symbol to say concentration of. So when you see this C here inside the big brackets, it says concentration of C. Now, concentration of C to the power C, to the power the balancing factor of C, times the concentration of D, the big brackets as you see it, to the power the balancing factor of D, which is small d, divided by the concentration of A to the power A, which is the balancing factor of A, times the concentration of B to the power the balancing factor of B, which is small b there, that B. Now, let's analyze this. If you check carefully, you will see that this Kc, it looks like the concentration and which are written as our numerator here at the top. It's actually the concentrations of the products. So you look at the concentration of the products at the top. At the bottom, obviously, you look at the concentration of reactants. Okay? But you don't have to forget that law there, how we express it. All this, you need to know how we express the Kc value. Okay? Now, there's something very important written down here. It says, if a reactant or a product in solid or in liquid, if it is in solid or in liquid phase, the concentration of such a substance stays constant during the reaction and therefore can be left out. Therefore, we don't have to put it into our equilibrium constant expression. Okay, we will look at some example. I think that is going to help us to see what is happening here. Right. So let's look at this example here. We want to write down or calculate for the equilibrium constant. Study the following reaction. We have got sulfur dioxide reacting with nitrogen dioxide. We have nitrous oxide or nitrogen monoxide with sulfur trioxide. All these are gases, okay? They are gases. Right. The concentration of the reactants are as follows. Okay? We have the concentrations here. There they are given to us. Calculate the equilibrium constant. Now, these concentrations here are the way they are when this reaction has reached equilibrium. So the concentration of the reactants and the products. So let me hasten to say that and the products here. All right? And products. And these concentrations are at equilibrium. Okay? At equilibrium. Okay? These concentrations are as follows at equilibrium. We have got concentration of SO3, 0.2 mole per cubic decimeter, NO2, 0.1 mole per cubic decimeter, NO, 0.4 mole per cubic decimeter, and SO2, 0.2 mole per cubic decimeter. All right? And we look like we're quite safe here because this reaction here is such that the balancing factors sort of one. Okay? We look at that point there. We don't have anything written there. And this chemical equation is balanced as it is. All right? And because it is balanced as it is, we don't have to put in any stoichiometric number or balancing factor there. And for that reason, it means the powers won't be there. Right, so writing our Kc expression for this chemical reaction at equilibrium would mean that we would have our Kc expression as follows. Remember, it is the concentration of the product. What are our products? NO is a product. remember there? And SO3 is the product, remember there. So it will be the concentration of NO, remember the big brackets mean concentration of, times the concentration of SO3 divided by the concentration of the reactants, SO2, NO2. Concentration of SO2 times the concentration of NO2. Now you would ask me a question to say, but where are the powers here? The powers are there. This is concentration of NO. There is NO to the power 1. Remember, there is a 1 there. So to the power 1, it stays as it is. Concentration of SO3 also to the power 1. Divided by concentration of SO2 also to the power 1. Concentration of NO2 also to the power 1. So all this is to the power 1. So I don't have to be showing all those things because they are all to the power 1. Right. Then let's work it out now. We may actually need a calculator here, but let's start by substituting here. What is the concentration of NO as given to us? It is 0.4. Okay, so for NO, I'm substituting 0.4 times concentration of SO3, 0.2. 0.2 mole per cubic decimeter divided by concentration of SO2, it's 0.2. Here is 0.2 there, right? And the concentration times the concentration of NO2, and what is that concentration? It is 0.1. Okay, and I can quickly find the answer here. Look at it. Mathematically, I know that 0.2 and 0.2 is going to cancel out. So basically, the answer here will be given by 0.4 divided by 0.1. Right, so let's use a calculator to find out what is 0.4 divided by 0.1. This is what you will be using, of course, in your exams and even in your practice work. So 0.4 divided by 0.1, what is the answer? The answer is 4. So the Kc value for this chemical reaction is 4. Now, I'm not putting a unit here. Why? Because Kc values do not have units. Okay? Kc values have no units. If you look at it, you're dividing concentration by concentration. So in a simple situation like we had here, you have got mole per cubic decimeter. You have got mole per cubic decimeter divided by mole per cubic decimeter. What is going to happen here? The units are going to cancel out and you're left with no units there. So the Kc value for this chemical reaction at equilibrium, in this case, is 4. Right, so that is how we can calculate for our Kc value. Now, I want us to go a little bit backwards and check on what happens. Remember, there were little rules on how do we write down our Kc expression. So we want to go back and check what happens when we have got solids and liquids as part of our chemical equation that is in equilibrium, and we are to write down the equilibrium constant expression, or sometimes even to calculate for it. But for now, I'm going to limit it to just writing down that that equilibrium constant expression. Suppose that we have a chemical reaction that is in equilibrium, and it involves calcium carbonate. So there is calcium carbonate, it's a solid. It reacts with hydrochloric acid, a solid, and this is in equilibrium. It gives us calcium chloride. This is in solution, and it gives us water. Okay, and let's just play with this and make it a liquid. And we also have carbon dioxide, which is a gas. All right. So that's what we have. If we were to balance this chemical equation, we have one calcium here, one there, CO3, I can say this CO2 then plus that one is CO3. Then I have H1, I've got 2 there, that's where I have a problem. I've got Cl1 here, I've got 2 here, that's where I have a problem. So by putting a 2 there, my chemical equation is balanced. Now, if I were to write the the equilibrium constant expression for this particular chemical reaction, following all the rules that is given to me, that there is no concentration for a solid and there's no concentration for a liquid, and therefore may not form part of my Kc expression. This will be given by, remember, it is concentration of products divided by concentration of reactants. So what do we have in products that has concentration? It's calcium chloride, because it is in aqueous solution, times the concentration of, can I put water? No, because I've got L there, it's a liquid. Then I've got carbon dioxide, gas, definitely. I can have carbon dioxide here as part of my concentrations of products there. So it will be calcium chloride times CO2. We can't have water, all right, H2O liquid. Then down here, divided by the concentration of reactants, calcium carbonate solid, can I have it? No, I can't have it. And because of that, I'm going to have my concentration right in the middle here, because I've got only one entity that I'm going to talk about. And there's, pardon me, this was just a mistake here. The HCl cannot be a solid. It's an acid, and therefore it is in aqueous solution. So that its concentration is actually taken into consideration. So that will be my Kc expression for this particular chemical reaction. So that's how I would write it. And if I know the concentrations of these substances at equilibrium, okay, their concentrations at equilibrium, then I will be able to take those values and plug them in here and calculate for my equilibrium constant value for this particular chemical reaction that is in equilibrium. Okay, now let's move on and have a look at another example. Now, example 3, it's one typical exam question, right? And it's something that learners battle with, and I want you to listen very carefully as we go through this one. It says 14 grams of ammonia gas is introduced into a sealed, in other words, sealed closed container, okay, or sealed vessel. The volume of that vessel is 2.0 cubic decimeter. The ammonia decomposes or breaks up when the temperature is increased to 600 Kelvin, all right, and reaches equilibrium as follows. Okay, so there is equilibrium reached here, and the equation is that one there. Now, upon analysis of the equilibrium mixture, so it reaches equilibrium and we analyze it, we find that the concentration of ammonia is 0.3 mole per cubic decimeter. The question is, calculate the concentration of N2 and H2 in the equilibrium mixture. Now, let's quickly write down what is given to us here. 1, we've got the mass of ammonia. That is 14 grams. We have got the volume of the reaction vessel. That is 2.0 cubic decimeters. We are also told that at equilibrium, so now at equilibrium, the concentration of ammonia is 0.3 mole per cubic decimeter. Okay, so that is what is given to us. And from this, we can work out quite a number of things. Now, let's start by looking at this equation here at equilibrium, and in the table here, what we are required to do. In the table here, we can now work out the molar ratio of our chemical equation here, or from the chemical equation. For ammonia, it's 2 there. For nitrogen, it's 1 there. There's a 1 there. And then for H2, it's 3 there. That's our molar ratio. Now we need to come up with the initial number of moles for each of this. And initial meaning at the beginning, when we start. From the beginning, we know that it is this ammonia that is breaking up. So as it starts breaking up, at the beginning, we don't have anything of that, and we don't have anything of that either. So we don't have nitrogen, we don't have hydrogen. So the number of moles of those two at the beginning is 0. Then the question is, what are the number of moles of ammonia that we're having? Well, from the given information, we can calculate for that. How do we do that? We know that number of moles is always given by the mass divided by molar mass. So that's one way of calculating number of moles, and this is the applicable one for this situation now. Why? Because we are given the mass, we are told is 14 grams. We divide it by the molar mass of NH3 now. Molar mass of NH3, how do we get that? Now look carefully now. N has got a molar mass of 14 plus hydrogen molar mass is 1, but we've got 3 of them, so it will be 3 times 1. The total here now is 14 plus 3, and therefore it is 17 grams per mole, right? So that is the molar mass of ammonia. And from this, then we can put the 17 in place of molar mass in this formula, and we can calculate quickly what the number of moles are here. Now quickly, using the calculator, we can do that. You see here we've got 14 divided by 17, and what's the answer? The answer is 0.82 moles. So we've got 0.82 moles of ammonia at the beginning. 0.2 moles of ammonia at the beginning. So we can fill up this part here for ammonia. We've got 0.82 moles. Now, we are also told that from this given information here, we are told that at equilibrium, the concentration of ammonia is 0.3 mole per cubic decimeter. Now, we also need to work out the number of moles from that concentration. Or perhaps before we do that, let's just slot it in. We know this is equilibrium concentration, so for ammonia is going to be 0.3 moles per cubic decimeter. So if we are to calculate for the number of moles at equilibrium, how are we going to do that? Now we know that concentration is given by number of moles divided by volume. So in this case here, the number of moles is what we are looking for. Therefore, the number of moles N will be equal to concentration times the volume. And what is that? Concentration is given to us is 0.3 times the volume. We are given the volume as 2.0 by 10 to the 2.0 cubic decimeters. So what do we have here as number of moles? It's going to be 0.6 moles of ammonia at equilibrium. So now we also have another solution to this one. That's 0.6 moles of ammonia. Now we can work out something from here. We can work out something from here. Why? Because if we started with 0.82 moles of ammonia, and at equilibrium we have got 0.6 mole, what has happened to the other moles? In other words, how many moles of ammonia has been used up? It will be this total number of moles of ammonia we started with minus this number of moles of ammonia that are present at equilibrium. So how do we do that? You can work out this quickly. Even if you're not using a calculator, you can see that quickly. Let's see it. 0.82 minus 0.6 is going to give us 0.6 0.22. So we've got 0.22 moles of ammonia that has been used up. And it is from this number of moles that we have got some moles of N2 formed and some moles of NH3 formed, because these ones remain unreacted. They are still there at equilibrium. So now, let's have a look at this ratio. See where the ratio helps us. If 0.6 moles of ammonia has been used up, we will have how many moles of nitrogen and how many moles of hydrogen formed. The ratio tells us if we have got 2, we will produce 1. So this one is always half of that, if you like. Okay? And how do we find that half? Sometimes you can say, let's divide through by this 2 here, because we're looking at ammonia as the given. So we divide by 2. This is 1. This is 1 over 2. That is 3 over 2. So you can say that the number of moles of, let me write that down quickly. The number of moles of N2 that has been formed will always be half the number of moles of NH3 moles used. Okay? This is what we have. We will always have it from that ratio. The N2 moles, let me write down here. Moles of N2 will always be half of that from the ratio. Let's also look at what happens to the moles of H2. That one, it's always will always be 3 over 2 of the what? Of the NH3 moles. Okay? NH3 moles used. All right. So this is what we get from the ratio. 1 over 2 and 3 over 2. Where does that come from? 1 over 2 for nitrogen, 3 over 2 for hydrogen. That's where it comes from. So let's work it out quickly. Number of moles that have been produced of N2. So for N2 moles will be equal to half the number of moles of of ammonia that has been used up. What is that number? 0.22. So half of 0.22. That has been used up. So what is the number of moles of N2? It's going to be 0.11 moles. Okay? 0.11 moles. Quickly, what will be the number of moles of hydrogen formed or produced? The number of moles of hydrogen formed will be 3 over 2 of the NH3 moles. What is the NH3 moles? It's multiplied by 0.22. That's the NH3 moles. So when you work this out, perhaps this you might need a calculator, but let's quickly look at it. 3 times 0.22 is 0.66, and divided by 2, it's 0.33, if you like. So that will be 0.33 moles. Okay? So we can work that out quickly. Right. Now, so we know this. This is 0.11. The other one is 0.33. So let's write that down quickly in the right space. N3, 0.11. NH3, H2, 0.33. That's what we have calculated down here, 0.33. Okay, so those are the number of moles. Now, let's now continue and fill up the rest of the table, because that's what we're working on. If you like, this, it's plus, it's what is added. This is also plus, it's what has been formed, what is added. But this one, the 0.22 is what has been used up, so we can put a minus here for it. So minus 0.22, if you like. That's the way you would want to work it out to see actually what is happening. So at equilibrium, which is the situation where we are interested in, at equilibrium here, what is happening? Here we have already found out from the calculation, from the information given to us, the number of moles of NH3 at equilibrium is 0.6. For this one, it will be 0 plus 0.11, 0.1. This one, 0 plus 0.33, it's going to be 0.33 moles. Now, equilibrium concentration. Concentration, again, is number of moles over volume. So what will be the concentration here? It's going to be number of moles is 0.11 divided by the volume is 2. And what is the concentration here? We can use the calculator again quickly. We have here 0.11 divided by 2. That is the volume of the vessel. And what is the answer? That will be 0.055. So the concentration is 0.055. The same thing here, C, concentration equals N over V, and that will be equal to number of moles. Remember here, we've got 0.33 divided by the volume. They are both inside a 2 cubic decimeter flask. And what will be the concentration here? So the concentration there will be, let's work it out quickly from the calculator. We're going to have it as 0.33 divided by 2. What is the answer? We get the answer to be 0.165. So the answer is 0.165. 0.165. 0.165 mole per cubic decimeter. So we have now answered this question. We were calculating or finding the equilibrium concentrations of nitrogen and hydrogen because we had the equilibrium concentration of ammonia. Okay, so we have done that. And one other thing that can happen to a question like this, you may also be asked to say, find the equilibrium constant. So it's something that you can actually do as well from this given information. Right, let's now move on to something called Le-Chatelier's principle. Now, Le-Chatelier's principle is a principle that talks to us about 3 factors that affect state of equilibrium. Those 3 factors are concentration, temperature, and pressure. These are the only 3 factors that affect a state of equilibrium. And what Le Chatelier is saying is that if a chemical system that is in equilibrium experiences a change in any of these ones, okay, the equilibrium will shift in order to minimize that change. So the change happens and the equilibrium shifts in order to minimize the change. Now, shifts. It's gonna, remember it's a reversible reaction. So when it shifts, when we talk of shifts there, we are saying it is either going to shift to the right or to the left. It's either going to shift in the forward direction or it's gonna shift in the reverse direction. So that's all about the shifting there. Now let's have a look at how this shifting actually happens. Okay, now these factors, like I've already explained, we're talking concentration, we're talking temperature, and these, when we talk concentration, we're talking about substances that are in solution form. In other words, those substances where the state is represented as AQ. At the same time, when we're talking gases, all right, G, we talk concentration here, number of moles per volume. But temperature affects everything. Now, catalyst, will a catalyst affect a state of equilibrium? We'll talk more about that. You know what this is. It's a substance that is used to speed up the rate of a chemical reaction. So we'll talk a little bit about it later on. Okay, now, let's look at example 4. hydrogen and iodine gas react in a sealed container with a fixed volume according to this chemical reaction here, which is reversible. After chemical equilibrium is reached, the number of moles of iodine gas is increased. So let's look at where iodine is. Iodine is on the left, and we are told that after equilibrium is established, the number of moles of iodine gas is increased. In other words, you've got equilibrium, then somehow you bring more of iodine moles. So you increase it. Okay? So when you increase it, what do you think is going to happen? Let's establish first what we mean by increasing the number of moles of iodine. Remember that the volume is constant there, it's fixed. But then you are increasing the number of moles. Okay? So if you're increasing the number of moles for iodine, this equation here that says concentration is equal to number of moles over volume. If the volume is kept constant and you are increasing that n there, the number of moles, you are actually increasing the concentration. It's getting up. Okay? So you have changed the concentration of iodine here. You have increased it. Now, what is the system here going to do to actually try and bring back the balance again? Because now the equilibrium has been disturbed by the increase in this concentration. So what is the system going to do? Well, I think fairly straightforward, we can see that this equilibrium as being disturbed, it is going to try by all means to get the iodine used up, reacted, so that this concentration is brought down, is decreased. By doing so, it will be using a lot of the H2 to produce the the hydrogen iodide there, which means the forward reaction is going to be favored. So the question here, number A, says, predict what will happen to the position of the equilibrium. The equilibrium will shift to the right. You see, equilibrium here shifts to the right. Why? Because it wants to level up the increase of concentration of iodine here. To do that, it needs to shift everything to the right. In other words, more of the hydrogen iodide is going to be formed. So equilibrium shifts to the right, or shifts to the forward, or towards the forward direction. Let me just call it to the right here. Okay? So that's what is going to happen. Question B says, explain your answer above by applying Le Chatelier's principle. Okay? Now, how can we explain that using Le Chatelier's principle? What we need to understand here is that the equilibrium has been disturbed. It has been disturbed by the increase in iodine concentration. Okay? And because that has been disturbed, now we're using Le Chatelier's principle now, then equilibrium shifts to the right in order to decrease the iodine concentration. Right, let's now look at the last part of this question, which is question number C. Now, C says, what happens to the value of the equilibrium constant? What happens to Kc when all these changes take place? Now, there's something that we need to understand about Kc. Kc, or equilibrium constant, is only, the value of Kc is only affected by change in temperature. So this is not yet the answer to this question. I'm just explaining it. So Kc is only affected by the change in temperature. Change in temperature. Every other change does not alter the value of Kc. So the answer to C will be to say that Kc remains constant. Okay? It remains the same. It is not changed. In other words, you must know that change in concentration, and pressure, these two do not affect or alter Kc value. Those two will never affect. But then it's only temperature. Change in temperature definitely is going to affect the value of Kc. Right, so that we need to know. Right, let's now look at example 5. Okay, example 5 says the catalyzed step during contact process. Now you'll remember contact process, the process that involves the manufacturing of sulfuric acid. So when that contact stage is reached, the chemical reaction that represents it is this one here, and it is a reversible reaction, and it can reach a state of equilibrium. And delta H, heat of reaction, is minus 198 kilojoules. Now we need to understand what this means here. All right? Now, when we say, before answering this, perhaps let's come back to this. If you are having a catalyst in a chemical reaction that is reversible, can you affect the state of equilibrium? No. A catalyst does not affect the state of equilibrium. All it does, it will speed up the rate of reaction. So in the same way that it will be speeding up the forward reaction, it will also be speeding up the reverse reaction. So what it does, it just makes the chemical reaction to reach equilibrium much quicker. And if that is what we want, and we are in industry and we are producing this sulfuric acid, so we want this stage to always happen, we can use a catalyst to quickly get it to work. But we are not changing how much of the yield, but we are doing this more often, because then the time is such that we are able to do this quickly than just sitting and allowing it to drag and take too long. That's all the catalyst would do. So we are told that the heat of reaction is minus 198 kilojoules. Now here are the questions. Is this reaction exothermic or endothermic? Give a reason for your answer. Look at it. This reaction is definitely exothermic. Why do we say it is exothermic? Because delta H has a negative value. A negative value means that energy has been liberated. So we have got energy liberated here, or given off. Okay? So that means that the reaction is exothermic. So that would have given you your answer in terms of giving a reason here. Why do we say it's exothermic? Because the value of delta H is negative. Value of delta H is less than 0. Negative. Less than 0. Okay. Now let's move on to B. How will an increase in temperature, now we are changing temperature, influence the concentrations of SO3? Now, temperature, what you need to know, temperature would always favor endothermic reaction. So temperature favors endothermic. Increase in temperature favors endothermic reaction. Favors endothermic. Okay? So we are specifically saying here it will be endothermic if you are increasing here. In other words, temperature, let me write it here, temperature increase. So when you increase temperature, you favor the endothermic reaction. Now, what is the endothermic reaction here? The forward is exothermic because delta H is negative. Therefore, the reverse is what is endothermic. Okay? So endo is reverse. So if we increase the temperature, what will happen to the concentration of SO3? SO3 is on the right, and increasing temperature favors the reverse. In other words, more of SO2 and O2 are being formed, and this one is actually breaking down to give us O2 and SO2. So this concentration of SO3 here is decreasing. So we will say that the concentration of SO3 will be decreasing. Okay, so the answer for B here is that the concentration of SO3 decreases. That's how the change in temperature in this case will do to the concentration of SO3. Explain your answer by applying Le Chatelier's principle. Le Chatelier's principle, look, the reverse reaction needs energy. It's the endothermic, it takes in energy. So if you put in energy, the endothermic side will want to use that energy up so that the disturbance is actually leveled. So the reason here, or the explanation we can give here in terms of Le Chatelier is that the added energy will be used by the endothermic reaction, which is the reverse reaction. Okay? The added energy in terms of the increase in temperature will be used up by the endothermic reaction, because we know exothermic reaction gives off energy, so it doesn't want to take more energy. What takes energy is endothermic. C, what changes can be made to the equilibrium system to increase the production of SO3? What can we do to push the equilibrium to the right? Now, let's look at the equation. Okay? One thing we can do, because the reaction rate to the equilibrium to the right is exothermic, we can cool off this. So we can drop the temperature. Okay, that's one thing. What else can we do? We can increase the concentrations of either SO2 or O2. We'll be pushing it to the right in that way. And what else can we do? I think that is actually what we can do. Those are the two things we can do. What we'll do is, one, we will cool off the reaction vessel. Okay, so we drop the temperature. Cool off the reaction vessel. Drop the temperature of the reaction vessel. Increase concentrations of SO2 and O2, those two. What else can we do? We can always remove. That's another thing that is coming to mind now. We can remove SO3 to decrease its concentration, so that the equilibrium would want to move to the right. That we can do as well. Then lastly, not necessarily lastly, number D, how will the addition of a catalyst influence the production of SO3? Definitely, like I said, the catalyst does not affect the state of equilibrium. So there will be no effect here in terms of the production. No effect. All it will do, it will make SO3 to be formed quickly, or to be formed at a faster rate. Okay? At a faster rate. Okay, so that's what it will do. Okay, now let's look at the last one, number E. How will the Kc value of this reaction be influenced if the pressure is increased while the temperature is kept constant? Give a reason for your answer. I have told you pressure won't change the Kc value. So Kc will remain constant. The Kc value will remain constant. Okay? Why? Because only change in temperature, only change in temperature will affect the Kc value. So only that will affect the Kc value, but if you change pressure or concentration, you're not going to change the Kc value. Now, that brings us to the end of this lesson. I hope you enjoyed it, and I believe you're going to practice more. It is very interesting. Do it over and over again. Practice on molar ratios, that table that we worked on. It's very important for you to practice different examples based on that so that you get used to it. Hope you enjoyed it. Keep well. From me, bye-bye.